So now we've seen that there are different kinds of infinity, but we have not so great intuition about them, and certainly pictures can be quite misleading. But so far, what we've got is just three kinds of infinity. We've got finite sets. Well, that's not a kind of infinity, but we've got finite sets. And we've got countable infinity. That's like it's based on the natural numbers. And we've shown that the rationals are also a countable set. And then we've got uncountable. And we've got this one example of the real numbers, or maybe an interval of the real numbers as well. Okay, but we haven't yet found two uncountable sets that aren't the same kind of infinity. So, for example, the plane seemed to be a candidate, but it turns out that the plane, or equivalently the complex numbers, or pairs of real numbers, or even triples or quadruples or n-dimensional space are the same kind of cardinality. They're uncountable, but they're the same cardinalities are. So we want to find two uncountable sets with different cardinalities. We want to see, is this the end of the story, or is there a whole hierarchy of infinities? In fact, there is a very interesting hierarchy of infinities. And it's the diagonalization trick that's going to come in again. So I showed you, I think, what I think is the most low-tech version of the diagonalization trick. I want to show you another version of the diagonalization trick to prove the same thing, that the decimals from 0 to 1 are uncountable, just with a little bit of a difference, and then that's going to translate to a much more general version of diagonalization. Probably the hardest part of these video lectures, I'm guessing, based on the response when I did it live. Okay, but the main thing is that the order for the real numbers wasn't really important. The idea of counting and decimals, that none of that was important. It's really just about sort of sets and yes or no and making correspondences. Okay, so the first revamp of diagonalization is to show that decimals in binary notation are uncountable. The whole 0 to 9 thing is really kind of a big red herring. It's like, well, what's special about base 10? Nothing. It's much more pure, and it'll translate better if we do the argument in binary. Okay, so you just have to believe that any number between 0 and 1 can be written as a binary decimal, just in binary numbers. Okay, so here's a binary number. This says 1 times 2 to the minus 1, 0 times 2 to the minus 2, plus 1 times 2 to the minus 3, etc. Okay, if you're not familiar with binary, look at it on Wikipedia a little bit. Okay, we've got you do the same kind of proof though. We assume we have a list of binary decimals. Okay, and one thing you might think is, wait, is it really important? These seem to be ordered. You just said there wasn't anything about order. Okay, the deal here is that the true heart, one of the big hearts of the diagonalization argument, is that there's a correspondence between the rows on the list. That's, we're assuming to get a contradiction that is that we can order the rows on the list or correspond the rows on the list to the natural numbers. And we know that there's a correspondence between that and the places on each list of zeros and ones. Okay, so we can think of this as a single number, or we can think of it as a list of zeros and ones. It's equivalent. And the key thing is that there's this correspondence. That's what allows us to make the diagonalization. Okay, because what we do is to list number 1, or number 1, decimal number number 1, binary decimal number 1. We highlight the first place. And in list number 2, we highlight the second place. In list number 3, we highlight the third place, etc. That produces this number. Now, remember what we do. We need to take this guy and flip everything. Well, with binary, that's particularly elegant because we flip 1 to 0 and 0 to 1. So we're going to create a new binary number, 0.0010, etc. So I flip the 1 to a 0, 1 to a 0, 0 to 1, 1 to a 0, etc. That number cannot be on the list by the same argument. It can't be in place number 1 because it doesn't match the first one. It can't be in place number 2 because it doesn't match the second, etc. And let's think about this correspondence. Remember, there was nothing super special about this being the natural numbers, the index list. It was just that when I say, does this number match the one in this slot, there's a correspondence between, slot number 3 means look at place number 3. And pretty soon we're going to replace these with more arbitrary labels that aren't numbers. In any case, this purifies the argument a bit and shows you that there must be a binary decimal that can't be on any particular list you put together. If you try to make a list of all these binary decimals, I can create one that's not on your list. Therefore, these are not countable. Okay, so here's the more general version. We start with any set, okay? And I'm going to not use numbers for the labels of the elements of the set because it's really important that it's not the natural numbers necessarily. It's not necessarily countable, so it could be the real numbers, and that's going to be one place we use it. The order doesn't matter. I'm just not trying to be too abstract, so we definitely want to have some explicit labels, but we don't want to think of them as it being special that they're in order A, B, C, D, E. Okay. Now what we do is we create a new set called the power set of S, and there's various ways to describe it. One way, and this is going to be corresponding most directly to the binary stuff we just talked about, is all the ways we can take every member of S and just put a no or a yes on each one. Okay, so this is going to be a somewhat complicated set. It's not a bunch of things from S. It's not something in P of S is not something from S. It's a way we can say no or yes for every member of S. It's a pattern of zeros and ones, no's and yeses, that are attached to everything in S. Another way to say it, and the way you'll usually see it if you Google power set or look at it in Wikipedia, it's a set of all subsets of S. So for example, suppose I wanted to single out the subset A, C, and E, and nothing else. Well, one way I would do that is I'd mark A with a yes, C with a yes, E with a yes, in other words 1, 1, and 1, and then mark everything else with a no, and we're going to use zeros for that for convenience and to make it parallel with the argument we just did. Okay, a pattern of no's and yeses is the same thing as selecting a subset. It's just the ones I said yes to. Okay, so if you imagine everybody in your business, your place of work, if you want to say what are all the ways I could pick some group of those to go out for pizza, I'm just going to look at, well, what are all the patterns of no's and yeses I could do? Yes to Bob, yes to Greg, yes to Carol, and they're going to be the pizza group and everybody else gets a no. Okay, so you might think that this is going to be a bigger set. If you start thinking about it, it's definitely going to include all the members of S just as one element sets. So I could just take A to pizza. I could just take B. I could just take C. But I could take A and B, or I could take A and C, or I could take A and B and C, or I could take D and E and G and K. There's a lot of ways to mark no's and yeses. So it's plausibly a bigger set than S, but we've been stung by that before. I don't think we should have any confidence right now, and we will in a few minutes, that this is genuinely going to be a bigger set. But it turns out this is the easiest way to create something that's guaranteed to be bigger. Okay, so we're going to try to run the diagonalization argument, and it turns out to work. We're going to start with the same kind of assumption for contradiction. We're going to assume that there's a one-to-one correspondence between S and P of S. Okay, the set of all lists of zeros and ones, or the set of subsets. Okay, and we're going to derive a contradiction to that, and we're going to see that P of S must have more stuff than S does. That's going to way to create a bigger set no matter what we're starting with. Okay, so let's write out part of that correspondence that we're assuming. Okay, so here it's exactly like the zeros and ones thing, but just with a bit of a twist. Okay, so I'm going to write out one list of zeros and ones. So I say here I'm saying yes to B, yes to C, no to A, no to D, and maybe no to everybody else just for simplicity to think about it. And here's another list. I said yes to A, no to B, yes to C, and maybe no to everybody else. So maybe that's just the subset, just A and C and nothing else. Okay, here's a subset with C and D, and maybe it has some other stuff, I'm not sure. Okay, so each row of this is a list of ways to say yes or no, or equivalently a subset of S. And the assumption is, well, let's look at the columns. Okay, so the column headers are which member am I talking about that gets a 0 or 1. So this is Alice, Bob, Carol, Dave. Okay, in this list, for example, in this choice of elements from the set, this way of saying yes or no, I happen to say yes to Alice. Okay, here in this list, this way of describing a subset of all the elements of S, I happen to say no to Alice. Okay, so that's what these headings mean. Now, the cool thing is that we're assuming that we can take a list of ways to say yes or no to Alice and Bob and Carol and everybody. We're assuming that we can match that up with an element of S, a person in our organization or whatever, some one of these labels. Okay, and so that's the big assumption. Oh, and I totally missed C here. That should be A, B, C, D, E. So anyway, it doesn't really matter for the argument, to be honest, but it's a little weird that I forgot to put C. Okay, so we're making this assumption, and this is what we're going to try to contradict. We're making the assumption that even though I've got a lot of these different lists, well, what if I could have a clever way of just saying, okay, this is a list of ways to say yes. It's a certain subset. It's a certain group to go out for pizza. What if I can just give that to Alice, and that will be Alice's list? And this will be Bob's list. And this will be, well, should be Charlie's list, but it's actually Dave's list, I guess. Okay. What if I could make that matchup? Then I get an amazing symmetry of this diagram, and that's what's going to make diagonalization work. That these list labels, assuming we can actually attach a particular person to each list, are the same as the labels up here, which said for each list, does that person get a yes or no? And it's that symmetry that's going to be crucial, because we can take the diagonal. Okay, we can take this list 0, 0, 1, 1, etc., and I can flip 0 to 1 and 1 to 0. Okay, that's going to define a list. Okay, can that list be on our list of lists? Can it actually be matched to a particular person's label? Okay, well, let's see. If I have 0 and 1 and 0, I flip this. Okay, I'm going to have 1, 1, 0, 0, etc. Could it be this list? Well, heck no, because I flipped that to be a 1, just like in the argument with the binary decimals. So, nope, that list is not on our list of lists. Can it have label B? Okay, I think about label B, and I think, what's the special place in the list to look at to see if it matches? And this is where the fact that there's a correspondence between the list labels and the original members of the set, that's where this is crucial. You say, oh, could it be label by label B? I'll look at position B in the list and see what it is. Well, this got flipped to a 1, and I look and I say, oh, you know what? That doesn't match. Whatever happens in the other positions, it doesn't match. Could it have label D? Okay, no, because I flipped that one, and etc. Okay, so it couldn't have any of the labels, because if I look at any particular label, I look at the corresponding entry, and I've guaranteed to have flipped that. Okay, so the assumption that I could match up list labels and actual people or members of S or whatever you want to think of this set as allows us to run the diagonalization argument. It allows us to create a new list whereby flipping these diagonals, and it can't have any label. That's our contradiction. That says that we can't have this correspondence between S and P of S. We've created a bigger set. There's got to be something more. Okay, so for example, we could apply this process to the real numbers. We get a strictly larger uncountable set, the set of subsets of real numbers, and then you can do it again and again and again and again. So at the very least, we're going to get an infinite family of truly distinct infinities, each one bigger than the last, even with this very loose notion, the cardinality method of comparing infinities. That's pretty awesome. We've got an infinite family of really very, very different kinds of infinity. And it even gets better than that, but we'll get to that by the end of the talk. Okay. So I want to talk about a few subtleties that come up, and some very famous subtleties, very, very brief discussion. Suppose we put those infinities in order, and notice that we're really kind of bringing in a tiny bit of ordinal thinking here. We'll call countable infinity Aleph naught. So that's the first letter of the Hebrew alphabet, Aleph. Aleph naught is the cardinality of the natural numbers, equivalently of the integers of the rational numbers. A lot of countable sets that we've seen. Okay, we'll call that Aleph naught because that's where we start. Let's call the next smallest kind of infinity Aleph 1. Whatever that is, it's going to be uncountable, but it's going to be the one that's just the next thing that's bigger. Okay, then Aleph 2, Aleph 3, etc. Okay. So you might think, oh, Aleph 1, you mean the cardinality of the real numbers, right? Because that was the first thing we created that was bigger, and then just recently we created a bunch of stuff that was bigger still. But the big question is the cardinality of R, the size of the real numbers, is that just the next thing beyond the integers, the Aleph naught? We know it's at least Aleph 1, because it's not countable, but Aleph 1 is defined to be the smallest uncountable infinity. And maybe this process that we did of creating the reals out of the natural numbers and this diagonalization argument, maybe it skips a bunch of infinities. Maybe there's actually a very fine-tooth system of different gradations of infinity that go in between the natural numbers and R. Or maybe there's at least one we missed. Okay, so is the cardinality of R Aleph-1 or not? Or is there some cleverer way to create just barely uncountable and not as big as how many real numbers there are? So is there a smaller uncountable infinity than the infinity that describes the size of the real numbers, the continuum? Okay. Well, Cantor didn't think so. Cantor thought, I've thought about this a lot. I'm the expert. Obviously, I invented all this stuff. He thought that probably R should have the cardinality of Aleph-1, that the next one after Aleph-0, the smallest uncountable infinity, should be a very familiar uncountable infinity, and by far the most useful, which is the cardinality of the continuum of the real line, the number line. Okay, so Cantor looked at this. I think he realized it wasn't proved, even at the start, although I'd have to check my history about that. And by 1900, it was pretty clear that it was a very important problem if you took these notions of infinity and set theory seriously. It's actually the first problem, I think, on David Hilbert's famed list from 1900 at the International Congress of Mathematicians. And so what happened in the 20th century? It's been 113 years since Hilbert brought it to light as a central problem, and even goes back further than that to Cantor. So what happened? Was it proved? Was it disproved? Did people not figure it out? Well, probably the most interesting possible thing happened to it. It wasn't proved or disproved. It was shown principally by Kurt Gödel and Paul Cohen, about 30 years separately from each other. It was shown to be independent of the usual axioms for mathematics. And I don't want to go into a big discussion of axiomatic set theory. But what that means is that given the usual axioms for mathematics that people found in the early part of the 20th century to be a very good foundation for mathematics, and it's based on set theory, again, goes back to Cantor, you can prove all kinds of things. You can figure out what's true, what's false. But there are some things that you just can't prove one way or the other. And Gödel was famous for showing a lot of this stuff. And in particular, he and then Cohen together, they proved sort of two halves of this result, said that given the axioms we usually use for mathematics, you can kind of come up with what's called a model of mathematics that satisfies those axioms where the continuum hypothesis is false, and you can come up with one where it's true. And so it's really independent. If you want to make it definite in your system of mathematics, whether that's a true fact or not, you actually have to add it in by hand. And that was pretty surprising, because people thought that given some simple basic axioms for mathematics, you should, in principle, be able to prove everything one way or the other. And this is a classic example of where that's not true. And the continuum hypothesis just doesn't have a definite truth value in the usual system of mathematics. Now, some people just say, okay, I want it to be true. I'm going to add it in, and then you're good. But you have to that's a much harder thing to convince people of than the usual axioms for mathematics, which are much, much simpler to state. Okay. So back to the ideas of comparing infinities and ordering the infinities. Okay. So there's going to be a least infinity, then a next least, then a next least, and Aleph-1 may or may not be R, depending on sort of what you prefer. It's kind of up to you, basically. Okay. And then Aleph-2, Aleph-3, well, etc. Okay. Is there like an infinite infinity? Is there some sort of limit to all these guys? How many infinities are there? It turns out to be a fantastically interesting, complicated subject, and pretty abstruse, to be honest. It gets very abstruse very quickly. Most mathematicians don't know very much about it, and I'm one of those people who don't know much about it. But I want to tell you a tiny bit about it. And the key thing is we've started to organize the infinities, even though the way we discover these types of infinity and the way that we tell them apart fundamentally is by the cardinal comparison method. We've started slipping into the ordinal way of thinking by putting them in order. Okay. Turns out that we can actually restart the idea of infinities completely using the ordinal comparison method. It's not as famous in sort of a popular level as the cardinal method, but it's very cool, And I want to give an introduction to the idea of the different kinds of ordinal infinities by talking about how they describe different styles of recursion, recursive algorithms, recursive calculations. And that's sort of where their main interest lies, is clarifying different types of recursion. So I want to talk about that starting in the next video.